Hello, everyone, and welcome to today's webinar on how to qualify cells and systems, cells for system and pack production. I'm Tal Sholklapper. I'm the CEO and co-founder of Voltaiq, and I'm here today with Dan Torelli, who's one of our senior battery engineers at Voltaiq. Just to recap the world we're in and why this is such an important topic. Historically, a lot of these were one-to-one relationships. Right now, it's a much more dynamic environment with a range of cells and cell oversupply. I showed this chart before, but it's pretty amazing to see the price decreases we've seen in energy storage. When I started Voltaiq about 13 years ago, everyone was talking about how we needed new technologies to get to under $100 a kilowatt hour. We're substantially below that point now, and really that creates an unlock of a range of applications that are now economical using batteries. And this prices are projected to continue to go down. And so that creates a question here, can you utilize those batteries, or even other questions, are those price points real or is this artificial? And I'd like to call out actually a post by Aaron Wade, who actually looked through the financial reporting from a whole range of the largest cell suppliers. He called this a myth. Cell prices are so low, they're probably selling these at a loss. And the reality here is, especially when you have these larger players who are at scale, are able to leverage those economies of scale and continue to grow their margins. And so they're selling these at pretty healthy margins, which implies that there actually may be an ability to even continue to drop these prices over time. And yeah, I encourage you to follow Aaron. There'll be a link here to his last post. He has some good content out there as well. And so low-cost batteries are here. They're mostly from China today, but others are catching up. The other challenge that we're facing is really around tariffs. And we already saw some of these early hiccups. There was China threatening to cut off supply to different economies. They made some noise about 10 years ago on cutting off supply to Japan for certain rare elements. So they brought it up recently with regard to the US. And now with larger tariffs and Liberation Day and all that mess, there's a lot of uncertainty now on exactly where your supply chain is going to come from, not only for the batteries, but also the raw materials. And so we're seeing this environment now where people have to be more dynamic. They have to qualify more suppliers. They have to be able to adapt to variation in their supply chain and different materials inputs. And that's going to create a lot of risk. And then just another fun point here, I was playing around with the different AI tools for image generation. The best one actually came out of Gemini, but as you can notice on some of the subtext here, definitely still get some quirks in there. So I encourage everyone to try these tools. They're pretty fun, and you get pretty nice animations with some good prompting. And so, yeah, there's uncertainty here. We've entered this golden age with low-cost cells. We have a lot of uncertainty here. People want to play across different suppliers to get the best deals. But at the end of the day, we have to make sure these things are going to be reliable and are going to meet our quality standards. And so just to recap, this is what happens when a lot of batteries light on fire all at once. This is Moss Landing over in California earlier this year. Basically, the entire facility burnt down, and this was from a larger Korean cell supplier. The other Korean cell supplier, Samsung, also had recalls earlier this year as well, affecting FCA, Audi, and Ford. And so it's not just one supplier. It was LG for the top one. Samsung, outside of the marketing around improves quality for the Note 7, still suffers with quality challenges. And then outside of that, even when ships are translating across the ocean. So this is a common problem across the industry, creates this larger ticking time bomb. So even if you can get the price point for your cells, get a cheap product that you put out there, if you have the safety issues at the end of the day or large warranty returns, it creates this larger time bomb essentially of your financial returns and creates a lot of risk for companies. So can't let that happen. So that's the whole point of this webinar, is how do we actually address this? And so going back, why is this all so challenging? And it really comes down to this challenge right now of people trying to get these products out the door quickly, take advantage of these economies, navigate the tariff environment while still maintaining quality. The challenge here is, as you go further on this process, battery qualification, these are living, breathing organisms. Unlike most components, we're not able to, with a quick spot check, see if they're good or bad. If a semiconductor, you could take a screen and very quickly flash it on and off and see if you have dead pixels. Batteries, those dead pixels are within this living, breathing electrochemical organism that has billions of those particles and pixels. And so those problems only surface over time, whether it's late in the production process or early in customers' use or all the way through fires in people's hands. And so that creates one of these larger fundamental challenges around batteries that you don't see in most other devices. The other challenge is even once you identify those problem batteries, you don't know what's affected. Is that just localized to that single battery? Was it abused? Something happened there? Or is this something more systemic? Is it everything that you produce, as we saw with the fleet-wide recall from Samsung? Is it something that is just limited to one production line on what day? And then what specifically caused that problem? Is it the BMS? Was it how it was assembled? Is it the materials? Figuring that out is really hard right now, just given how disconnected all the data is and the thousands of different things that can cause all of these problems. And so if you look at it as far as the larger life cycle of these battery systems, it is substantially cheaper to catch these issues earlier on in the process. So if you look at an outgoing cell from a cell supplier, of course, we want to catch things earlier upstream there. But when they come to the OEM or assembler who's putting this all together, you have initially that cell that was just shipped, you have the shipping costs. If you can catch that in incoming inspection, it's still pretty cheap to catch and remedy those issues. Once you assemble that into a module, pack, rack, cube, whatever you want to call it, and that final system, you have all of the bill of materials. You have the system, you have the thermals, you have everything else within that system that is now much more expensive with, instead of a single battery, now tens, hundreds, or thousands of batteries in that system. And substantially more expensive. And then once you get to the field, again, much more expensive. Not only do you have insurance and liability issues with customers, except for in spite of just the returns, but you also have a lot of the broader concerns around truck rolls and other issues there. Really, it's great that we have this optionality in new low-cost cells. We have a lot of opportunity here to look at different options within the supply chain, but ultimately we have to make sure these products are going to be reliable. And so leading into Dan's part of the presentation, we'll actually start diving into the meat of it. The question is here, how do we actually maintain optionality around all these things while continuing to ensure quality? We boil it down to three key points here. One is that you're going to have to expand your qualification programs. So given what the nature of how the battery ecosystem is and the uncertainty around tariffs and global trade, you're going to need to dramatically expand how big your qualification programs are, whether it's for cells, for packs, for materials, to have that flexibility to ensure that you could release your products. You're also going to need to continue to qualify if there are subvariants. Let's say your supplier has to all of a sudden switch a cathode supplier because they no longer have access because of trade restrictions. You're going to need to make sure that's going to meet your warranty requirements, and continue to stay on top of that and build up those programs and competencies is going to be key. Next up is when you actually decide what suppliers to use, is ensuring you have the supply agreements that cover you for those changes. Do they have to notify you if they switch that cathode? Are they giving you the right cells? Are those going to meet their warranty requirements over time? And this is actually going to be the topic of our next webinar coming up in about a month. And then finally is utilizing battery intelligence or digitization and tools to allow you to actually speed up these cycles, learn from these batteries faster. We can't just wait to qualify something for 10 years before putting it out in the field. And so you need to utilize data and analytics to really allow you to do that all at speed. And so with that, I'm actually going to pass it over to Dan.
Yep. Oh, good. Thanks, Tal. So I figured just to get started, we should get everyone on the same page and start by defining what cell qualification is and talking about why it's so important. So cell qualification is basically answering the question, does the cell meet my performance and lifetime requirements and the specifications that I have for my battery pack? So this is going to involve a significant amount of electrochemical testing, as well as safety testing and postmortem analysis. And we'll get into all that good stuff on the coming slides here. But why is cell qualification so important? Firstly, it ensures that the cells you're going to get are going to meet your requirements, but it's a lot more than that. It's about gaining a deeper understanding of how cells age, how quality and performance vary lot to lot, and understanding the weak points in your cell so that you can design against it. So let's say, for example, you're performing a temperature dependent study during your qualification testing, and you find out your cells are prone to significantly accelerating aging at high temperatures. So just knowing that information you can design your pack to have improved thermal management. Maybe you could derate your pack to operate in a more narrow temperature window, or maybe you can just choose cells that have better performance at high temperatures because you don't want to add thermal management into your pack. But whatever decision you decide to go with, your qualification testing is going to be the key source of data to make those decisions. So we talked a little bit about answering this question: does this cell meet my performance and lifetime requirements? Well, let's talk a little bit about what those requirements might be. So there's a number of different variables that are going to play a role in the requirements for your cells, and these are primarily going to be driven by the application. So for example, if you're making an electric vehicle, you have some requirements that, that look something like this as just an example here. You're probably going to be looking to purchase cells that have really good cycle life, maybe a high charge rate so that users can charge their car as fast as possible. But if you're making an electric power tool battery pack, you probably don't care as much about cycle life or charge rate, but instead you want cells with really high discharge rate and high power output. So it really depends on the application that you're looking at. While you're determining these requirements and making these decisions, though, it's important to keep safety at the forefront of your mind because you're going to be making safety critical decisions here. And so you need to decide on things like, how am I going to handle thermal management in my pack? How am I going to ensure that cells stay within their operating temperatures when they're discharging at high rates? Or how are you going to protect the cells from thermal runaway propagation? If one cell goes into thermal runaway, the cells in the pack need to be designed in such a way that those hot gases or ejecta from the cells will not cause other cells to go into thermal runaway. By the way, there's also one obvious one missing here, which is price. Obviously, price is going to play a big role in this decision as well, but yeah, not listed here. Okay, so now you've made some decisions about your requirements. You probably have a pretty good idea of what form factor you're going to use, as well as some of the suppliers you're going to be targeting. So once that's happened, you start to gather a list of suppliers that are making cells that meet those requirements, and then you can start gathering these spec sheets. So these spec sheets are going to have information such as the safety standards the cells are tested to, as well as information about the performance of the cells, such as min-max voltages, max charge and discharge current, capacity as a function of discharge rate, and some other useful information as well. So this is all really valuable information, but there's a lot of issues relying on these spec sheets alone. I think the first kind of most important one is that these can be theoretical or best case scenario performance criteria, and they may even represent a battery that hasn't actually been built yet. So they don't really tell you anything about the quality of the cells or lot to lot variations or anything like that. They also don't always contain all of the information that you need. And almost certainly don't include testing or information that's specific to your application. A lot of times they're PDFs, they have graphs that are just images, so it's really hard to compare one supplier to another, especially if the metrics that they report are slightly different or if the charts and stuff aren't scaled exactly the same. And there's a lot of variations from supplier to supplier in these spec sheets, making it really hard to compare apples to apples. So there's got to be a better way to do this, right? The answer is yes, of course. There are lots of better ways. So modeling is one kind of option you have here. And just to jump to the punchline here, no, you can't just do modeling or simulation. A lot of people see this kind of as a way to maybe get around some of the onerous testing requirements that you might have to do to qualify a cell supplier. And developing a good model can help you predict the lifetime of a cell, maybe a little bit of information about how it's going to fail, but you really need to go beyond that. And more than that, the battery failures are the result of variations in manufacturing process control and minor defects in underlying cells and materials, components, packaging, etc. And defect rates can range from parts per thousand to parts per billion. And so simulations are not going to catch those minor, infrequent defects that might arise in your cells that you're getting from your supplier. And so the simulation might tell you about the median cell or the average cell, and maybe plus or minus some standard deviation, but those aren't really the cells you need to worry about. It's the outliers that can kill you and the ones that you need to be considering when you're choosing your cell supplier. So really the only way to understand this is to collect and analyze the data and actually measure things and figure out how these cells are going to perform. Okay, so when you're doing that, you're going to be doing lifetime testing. As I mentioned, this is a lengthy and resource intensive process. It's going to take a significant amount of time, money to get set up. It's going to take a long time to run the test. And then you need to get the data analyzed. And oh, by the way, you need to do this. You need to have this design validated in a certain amount of time so that you can choose a cell supplier and go into production and you're not wasting time. So the question becomes, how can qualification testing be optimized? And that's one of the questions we're going to aim to answer here. The first thing you can do to optimize this testing is to start with kind of a quick initial screening of your suppliers with something like a rate testing to help rule out or in some of the suppliers from your list. And then you can move on to more resource intensive testing. So what exactly is rate testing? Rate testing is a type of electrochemical test that sort of maps out the battery's ability to charge or discharge at different currents. So in the example I'm showing here, I think this is like a 1 amp hour cell being discharged at 5 different rates from like 0.1 C up to 2 C. And then it has the same constant current, constant voltage charge step after each discharge step. And so again, just to keep everyone on the same page, I'll probably use the term C rate several more times. This is just a shorthand expression for normalizing charge or discharge rates by the capacity of the cell. For example, a 1 C discharge means the battery will go from 100% to 0% in about an hour. A 2 amp hour cell would discharge at 2 amps, and 150 amp hour cell would discharge at 150 amps at 1 C, and then so on and so forth. And lastly, it's important to note that this type of testing is normally repeated across a range of operating temperatures, which have a strong impact on the discharge capacity of the cell. So as many of us have probably experienced, a battery on a cold day can last somewhere between 10 and 30% less time than it would on an average day. And if you're in extreme cold, -10, -20 C, it's going to be significantly less than that. So doing this type of testing at a range of temperatures is really useful. Okay, so now you've done some sort of pre-screening of your cells. You've chosen your suppliers that you want to do long-term qualification testing with. And so now you need to figure out what this test matrix is going to look like. So let's say you've got a group of maybe 4 suppliers you want to look at, maybe 3 different lots of cells to get an idea of lot to lot variation within those 4 suppliers. So you've got about 12 groups of samples that you want to do some sort of testing on. The question becomes then, what kind of qualification testing are you going to do? So almost certainly you're going to be doing cycle life testing, and you probably want to look at worst case conditions. So fast charge, high temperature, fast charge, low temperature, 100% depth of discharge. But you also want to get an idea of more average or realistic aging conditions. So you might do a slow charging cycle or even a drive cycle life test if you're looking for EV applications. And you probably also want to test at an average temperature and partial depth of discharge to get an idea of less aggressive aging conditions. So if you do a fast and slow charge, 3 temperatures, 2 depths of discharge, you're looking at about 12 test groups there. You're also going to do calendar aging. So previously we talked about cells. We want our cells from our supplier to last for 10 years, but you're probably not going to be doing 10 years of calendar aging. So you need to find some way to either accelerate that or extrapolate the results from a shorter test to try and understand what the calendar age or the lifetime of those cells is going to be. And you'll probably look at aging as a function of SOC and temperature there as well. So if you just choose 2 SOCs, 2 temperatures, you're looking at 4 test groups there. As we discussed earlier, there's also rate testing, which can be done on its own or part of another test to improve efficiencies, which we'll talk about in just a bit. But you're almost certainly going to be doing rate capability testing to understand how a new cell, a slightly aged cell, and a cell towards the end of its lifetime perform with respect to discharge capacity at varying rates. So if you're doing this test by itself, you'd probably do at least a fast and slow charge while varying the discharge rate, maybe look at a few different temperatures, which would be 6 test groups there. Then after all that, you need to evaluate the safety performance of the cells. All of the suppliers should have done some level of safety testing, at least if they're going to be able to sell and ship them, but they won't have done any application specific testing. So if you're in the automotive industry, these are some of the standards you might test too. Some of these are on a pack level as well, but the cells certainly play a role in that performance of those pack level tests. And then lastly, you're probably going to want to do some sort of bespoke safety tests. And there's a number of different ways you can do this. Accelerating rate calorimetry is certainly a great way to understand heat release rates, onset temperatures for thermal runaway. You could do cell-to-cell propagation testing, again, to make sure that failure in one cell doesn't propagate to other cells, as well as looking at new and aged cells, which has a pretty big impact on the safety performance of the cells. And you're probably going to want to look at a variety of SOCs for those tests as well. So just those top three groups there, the cycle life, calendar aging, and rate capability testing from 4 suppliers, 3 lots of cells. It's 264 test groups. That's not even considering the safety ones. So you can imagine that's a lot of data you have to collect and analyze. And that's not even considering statistically relevant sample sizes. So you're going to be doing a lot of testing. You're going to be generating a lot of data. So how can you make your life easier and reduce the number of tests required? So reference performance tests, or RPTs, is a great way to do that. So this is basically combining multiple tests into a single test protocol. And the example I'm showing here, this is some raw time series cycling data, which shows a cell cycling at 3 different rates with some pulse testing at the end here. This is a good example of a cell being cycled to understand how its performance will change over time. We're also looking at how rate capability changes and how its internal resistance changes by using these RPTs every X number of cycles. You can also make a visual to look at the protocol that is being used by making a plot like this, where we're showing kind of C rate versus cycle number. And you can see that we're gradually stepping up that C rate every 3 cycles. Okay, so now you've decided on your suppliers. You've got a test protocol that includes lots of good RPTs, and you're about to start running your tests. But you want to make sure that you're extracting the most value from these extremely resource-intensive tests that you're going to be investing in. So you ask the question, is there anything else that we can do to get more value from these tests? The answer is yes, there is. So cell qualification is a unique opportunity to correlate kind of initial KPIs with a cell's end of life performance. So thinking ahead here, when you move into production, it's going to be really important to have confidence that the packs you're building are going to meet the warranty requirements that you set, and having the data to back that up. Part of the manufacturing process is going to be incoming quality control step, which helps to ensure no low quality cells are making it into your pack. The problem is there are probably tens of different tests and test methods out there for IQC, and knowing which test and what conditions to test is impossible without having the data. But some potential options are pulse testing, which looks at internal resistance and power output. You could look at self-discharge testing, which looks at the voltage of the cell over time to see if there's any defects causing the cell to self-discharge. Simple OCV measurements can be considered an IQC step and can be useful to screen out lower quality cells. And you could do like a partial cycle. You could do something like EIS or something a little more sophisticated like CT or ultrasound. You're probably not going to be doing CT and ultrasound on every single cell that comes in, but certainly they're very powerful predictors of cell quality. So we obviously don't have time to dig into all of those different tests, but I did want to highlight one in particular that has a lot of value and is relatively easy and fast to perform, and that's pulse testing. So when optimized appropriately, pulse testing can be a very powerful tool to help measure the quality of a cell. And you can look at the voltage change under a set electrical load and then calculate an estimate for the internal resistance of the cell. So here we're showing DCIR values calculated from a pulse test grouped by the different cell suppliers. So you can see supplier 1 is a little bit higher average DCIR, maybe even a few outliers up here that are out of spec. But if those outliers were filtered out, the spread of this might not be as large as the spread, say, from supplier 3. But doing these tests is not that simple, and you need to optimize the process so that it's as efficient as possible if you're going to try and do this during mass production. So conditions you can change may include pulse height, width, direction, what SOC the pulse is being done at, how long you need to wait in between pulses or the rest time, and then also the metrics that you extract, such as the DCIR, power, relaxation, voltage, pulse hysteresis, or nonlinearity, are all potential KPIs that you can pull from the pulse testing that could be used to estimate the quality of the cell. So take this unique opportunity explore a range of different potential pulse protocols and KPIs that could potentially be used when it comes to IQC. Okay, so the common theme throughout this webinar has been getting the most out of your data. I just wanted to show a few methods of doing this. So here we're looking at charge and discharge curves of a single cell at varying C rates to get an idea of what that voltage profile looks like and how the capacity changes as a function of C rate. You can also summarize this data in scatter plots, looking at the capacity of each cycle at different C rates. And so in this example, you can see that this cell from about -1C to -8C, there's very little difference in discharge capacity, which is great. But if you go up to 9 and beyond, you see the capacity really starts to take a hit. And so you're probably going to want to operate in that 1 to 8C range. If you've incorporated the effects of temperature into your testing, you can also look at how that changes the voltage profile and the discharge capacity of your cell. So here we can see that between 25 and 40 C, there's very little difference in the cell's performance, but at 0 degrees C, and especially at -20, there's a pretty significant drop off in cell capacity. And so that'll help you hone in the operating temperatures of your cells. And then lastly, you can look at differential capacity or DQ/dV plots of the cell at varying C rates to understand kinetic limitations of your battery, particularly increased IR drop, solar ion transport, and things like that will be brought to light by DQ/dV. Okay. Lastly, it's important to know there are literally dozens of KPIs that you can extract from your qualification testing, including those listed here. You can visualize them in different ways, but no matter which KPIs you're using to evaluate the performance of your cells, you want to make sure you're analyzing things holistically, looking at a range of KPIs, evaluating how those KPIs change over time or as you cycle the cell, and decide which ones are the most important for your application. So here we're showing some different types of plots you can make that show a range of KPIs. These are all metrics that Voltaiq calculates automatically as the data is synced and processed, making it really simple to diversify your analysis. Okay, so everything leading up to this point has focused on extracting the most from your qualification data and all the metrics and analysis you can do beyond sort of simple discharge capacity over time. But there's a reason, there's a lot of value in capacity versus cycle plots, and there's a reason that this is everyone's favorite plot to look at. But it's important to know the best way to perform these tests and the best way to analyze the data from them. So the first thing to note is to cycle the cells until failure. So in theory, you can in theory cycle them until they've hit a warranty requirement or some end of life condition. But if you stop cycling there, you won't necessarily know how long that would have lasted or if that cell was about to fall off a cliff. So it's important to cycle the cells until they degrade to a certain sort of predetermined amount. Next thing you want to keep in mind is you want to compare suppliers with statistical significance in mind. So you don't necessarily just want to look at the average or best or worst performing cells from a supplier, but rather look at this all together, as well as standard deviation, presence of any outliers, failure modes observed, to give you an idea of how those suppliers compare to one another. So here we're showing how the capacity fades with increasing cycle counts down to about 80% capacity, which was the original capacity. And then we also have some box plots to look at the spread of that data. And with that, I want to do just a quick demo here to kind of show you how one might do this analysis in the platform. Switch over to my Voltaiq window here. Hopefully you guys can all see this. So I've got some cells here that have some cycle life testing and a bunch of different RPTs. So you can see this graph looks quite noisy because I have all these RPTs because I thought this would be a good idea, but now I want to make a plot and my plot looks really ugly. So you can do some things like adding some filters down here. It's really easy to just filter out mean discharge current, less than some threshold. Think about 4.5 amps should do it. So now you're able to quickly filter out those RPTs and get the plots surrounding those RPTs. But also, you don't necessarily want to look at the individual cells. You want to look at the cells that are an average from that supplier. So you can add some grouping there to group the suppliers together. So a legend on here so we can see that. So you can see the LG versus Samsung cells pretty easily there. Maybe you don't want to just look at discharge capacity though. You want to look at state of health, or you want to normalize for a certain reference cycle. So maybe reference cycle 2 is a good one to normalize for. So now we're looking at discharge capacity normalized for cycle 2. You can see this is now a percentage. You could add some annotations as well. So I want to add an overlay here, look at discharge capacity. I want that to be 80%. It's going to go off my screen, which I'm going to fix in just a second. And then go down to maybe 70, 105. And now you can see that those cells went 600 cycles and didn't hit that 80%, mark that we hit there. So that's just a good quick overview of how easy this can be done in Voltaiq. Going to bring my webinar back up. Okay, great. So you cycled your cells until they failed. You've done your thorough analysis. You might think you're done, but you're not. And it's really important to conduct a thorough postmortem analysis in order to understand how the cells fail. So part of this can be gleaned from those appropriate RPT tests that we've done throughout. This could include the rate testing, pulse testing, maybe EIS testing throughout. You could also look at self-discharge at the end of life. So just measuring that OCV over time to see if the cell is going to be discharging faster now that it's at its end of life. You could also do something more sophisticated like CT or cell teardowns to understand how the cells have aged. And lastly, as we mentioned before, doing some safety tests on those aged cells can be very valuable information to have. And so we're quickly running out of time, and I do want to save some time for Q&A. So I think I've got 2 slides left here. I'll go through them quick. But just with respect to safety testing, there's a lot of standardized testing you can do. UN 38.3 is the bare minimum. Most cell suppliers are going to do that on their own. There's a few others that are industry specific that look at the cell's performance within the pack. So things like IEC 62660, and there's some SAE and UL ones as well that are good standardized testing to do. But it's important to remember that standardized testing does not necessarily guarantee a safe or reliable cell. And it's really important to go beyond the standards. So doing things, like I said, new versus aged cells and understanding those differences, looking at ARC testing, accelerating rate calorimetry to understand heat release rate, onset temperatures of thermal runaway, thermal management requirements for those cells. All that's really valuable information when you're going to go put these cells in a pack and try and have them last for years of cycling. And then lastly, you'll obviously want to evaluate these cells in the packer system. I think this gets in a little bit into validation, but the specific cells that you choose are going to affect the pack performance and design. And things like cell binning, cell balancing, the cell supplier that you choose and the qualification testing that you do can potentially affect these types of decisions. Thermal management, BMS design, voltage monitoring, all that good stuff is going to play a role here, and the cells that you choose will affect these types of decisions. And so lastly, just plug what comes beyond qualification. As we mentioned, cell validation or system level, pack level testing is important, but you also want to have kind of the right agreements in place to make sure that you get the cells that meet those requirements. And so that'll be the focus of our upcoming webinar. And then we'll talk about going into production and how you can ensure that the cells that you're purchasing and putting into packs meet those rigorous quality standards that you set during your qualification testing. So just quick summary, make sure to pre-screen your suppliers, whittle it down to only a few that you're going to invest the resources to do long-term testing in. Combine your tests, so do cycle life testing with RPTs, run them at different temperatures, get all of the data out of it that you can so that you're maximizing those efficiencies. Real-time monitoring of tests is really helpful as well. If you can keep an eye on things, you can end them as soon as they reach end of life, which will help improve some efficiencies there as well. And then lastly, determine what are good predictors of end of life performance.
Awesome. Thank you, Dan. And I love how you worked in the demo in the middle there. Just show people how easy it could be. So it is a lot of data, and just staying on top of it and looking across different suppliers, different tests, gets challenging. So we're going to move into our Q&A section here. Before we do, we're going to put up a quick poll. If people are interested in getting in touch, we work with dozens of companies across different parts of the supply chain. And if people are interested in getting in touch, definitely submit and put your information there. Happy to follow up with some of our team. And with that, I think let's dive into some of the Q&A. So yeah, I think there was a fundamental question here around, isn't this just validating what the supplier should already be telling you? Shouldn't this be obvious at this stage? And yeah, I just want to start off the discussion here really on that topic. What is that challenge? Isn't this something that should already be solved when you sign the supply agreement, buy from your supplier?
Yeah, absolutely. It is basically validating what the supplier says. In all fairness to the suppliers, they can't necessarily anticipate the pack design you're going to use, the application that you have in mind, and it would be impossible for them to test all of their cells to all applications that they might one day be used for. And so they have to do very generalized testing. They're obviously going to put their best foot forward when coming out with these spec sheets. They're not going to tell you like, oh, by the way, 1 in a million cells might catch fire in your car. Just a heads up. Yeah, those spec sheets are a really good place to start. That's how you're going to choose your suppliers. But then when it comes down to actually doing the testing, it's all about verifying those claims and really testing a lot of samples too, right? Like we mentioned, there's going to be really small defect rates for most of these suppliers, not necessarily saying that you can test enough cells to catch those defects in your qualification testing. But if you see large spreads in performance, if you see outliers, underperforming cells, those are indicative of lower quality production processes. And so just having that data and understanding on those deviations from what you expect, that's really powerful information to have when you go about putting these cells into packs.
Yeah, so I think a couple things are key in there. So just first up, as Dan said, they're not testing for your specific requirements unless they're making a very custom cell exactly for you. So unless it was designed for you and you're getting a generic cell, they are testing at standard C rates, 1C, half C, or something like that. They're going to test at a handful of rates. But for your specific application, you actually have to think through what are those power profiles that you need to support. What do you actually need to be testing as you put it into a system? And so that's on you to really figure out if that battery can meet your system specific applications as system requirements. And then the other part of this is actually taking those cells and integrating them into the system. So you need to run a lot of these tests also to generate the data that's going to help basically feed into your modeling efforts as you decide how to assemble these into a larger pack, figure out the thermals, figure out the electrical BMS and all of those other components. And then the other point, you have this larger question, what is statistical? You're not going to be able to catch everything here. What you're really looking for from this qualification testing is really understanding the spread in these batteries around your specific application requirements. And then it is on you to work with other data sources or your supplier and require that they look at that spread in production. If you're starting to see cell to cell, like we have 5% spread in initial capacity, is that okay for your warranty requirements, or is that going to cause problems for you? You have to decide what's acceptable, what's intolerance, and really start to dial that in. And luckily in the production process for cells, also for modules and packs, we are constantly recording data on these batteries on all the end of line processes. And so it's really about leveraging and getting access to that data so that you can do that analysis and have the systems that do that automatically. So yeah,
that's a good plug for the last webinar, which will be
yes.
which will be on that exact topic.
And then yeah, the other thing is just I think a lot of people try to short circuit this process. Let's come up with an optimized design of experiments. I'll only do edge points around these things. Those edge points are good as you're trying to provide inputs and features that are going to go feed into your models. But ultimately, you need to run a decent amount of statistics around some of those points in order to really start seeing that statistical variation so that, what you need to design tolerances around for the broader pack or system as well. So let's see, other questions in here. Safety standards, I think we talked through those. Dan walked through some of the standards as well.
But yes, there are third parties that do the testing and create some of these standards specific for those applications. But again, it really comes down to testing your actual design in your pack. And so, for example, if you're doing cell to cell propagation testing, there are standards that kind of dictate how that should be done, but it really depends on the actual pack that you're testing and how that's designed, how you're going to instrument it. And so all of that is bespoke and tailored to your specific design.
Yeah, and that's really it, actually thinking through. It's not just, can't just give you a formula. It's here's a spreadsheet, here's what you should test. It's thinking through, once it's put into a system, what are those failure points and what do you need to test for? What are your power requirements for the vehicle? And really trying to figure out around those how to dig in to all this information. Let's see, questions about electrode quality. So yes, a lot of these issues ultimately come from electrode quality. Are suppliers looking at upstream data on electrode loading, defects, slurry mixing, and all the other rheology that comes out of that? I think Dan could likely talk to some of that as well.
Yeah, absolutely. Certainly the cell manufacturers are doing that type of analysis routinely. We work with them to help do that sort of analysis. And this will be a little bit touched on in the third webinar as well. You as the purchaser of those cells, as the OEM, have some skin in the game. You have the ability to negotiate things like a factory audit, where you can go and walk the manufacturing line and ask questions like this. How are you guys measuring your mixing process? What kind of KPIs are you looking at there? How is that being tracked? How are you tracing cathode roles to cell IDs, and how are you quarantining cells when an issue is identified? And there's a number of different things that you can look at during those audits, but certainly you as the OEM have the ability to do that, and it's highly encouraged.
Awesome. And there's a question here about high-level guidance for how to sort for production assembly based on incoming quality inspection. And that's actually going to be our fourth webinar as well. We'll dive deeply into that, but reach out if you want to get in touch ahead of that. And then, how do manufacturers validate thermal management systems to prevent overheating in large-scale battery packs? Yeah, it ends up being, I'll start here. It ends up being a multi-pronged effort. So usually it starts off with take and measure cell data. You extract parameterization or metrics from those cell tests where you have some thermocouples and start looking at how the cells are heating themselves. Someone will then take that and use that in a model to basically come up with the pack design and what the pack thermal requirements are going to be based on the cells. And then ultimately you end up validating that in a completed pack to make sure that you're stay within the right window that is not going to age your cell too much. The big problem with overheating is as cells get very hot, that is one of the largest causes of degradation and early lifetime failure of batteries. And so that is one of the key considerations here. And so at the end of the day, you have to go and take those packs that you designed, actually build them and test them. And what you end up seeing in a lot of the larger OEMs is what's often called instrumented packs. So in the final vehicle, you're probably going to have, you're trying to get the price point as low as you can, so you'll have as minimal instrumentation as possible. But in the development process, you'll see packs with sometimes tens or up to thousands of different thermocouples embedded within them, so you can really assess those thermal gradients, see if there's any hotspots. So it is an iterative process, and it does start with that. I think that chart Dan showed near the end, we're going through the different stages of product development. Starts with early qualification at a cell level, and then you model, build the system, validate, and then finally get to production. So it is an involved process, and happy to walk through that also in a follow-up session.
Yeah, and I think the only thing I would add there is, again, it's important to evaluate these systems as they age, right? The thermal management requirements of a brand new cell coming off the line are probably going to look different than one that's been through a few thousand cycles or is a few years old and the resistance has increased over time. So it's important to remember that these cells will get hotter over time. They will age faster. As they age, they'll degrade more. Evaluating cycled cells and packs as well is important for that.
Awesome. And we have a question here about secondary analysis like DVDQ and DQDV and differential capacity. So yeah, that is a big part of what we help customers do. One is just automate their standard capacities, energy, some of the stuff that Dan showed. He actually had a plot with DQDV there if it was missed earlier. But yeah, there's about 80 or so metrics we compute automatically right out of the box. And then there's additional visualizations and metrics that we configure for customers to look at differential capacities, to look at a whole range of kinetics and other metrics that you can extract from this data. And I'd recommend, if people are interested in that side of it, we actually ran a webinar series recently with Novonix. Those are also on our YouTube, that walks through the combination of these metrics more broadly, and then what that looks like even with high precision coulometry equipment as well. It goes into a lot of those basics, including things like, yes, cell suppliers are not going to give you Git and PIT analysis for diffusion coefficients. And there's a lot of that you could actually extract from your existing test protocols, but also some of these pulse power HPPCs and other pulse power characterizations and others. But I encourage you to watch those webinars to actually compute those. And a lot of people actually go through the effort of tearing down cells and doing additional measurements as well. So there's a lot you can do without the teardowns. You can get a lot of that data just from the same testing you're doing today. The multiple ways to dig in and get continuous more information there about the devices.
Yeah. I think the only thing I would add to that is with respect to the secondary analysis, it's certainly something we do and encourage. As we mentioned, there's probably hundreds of different KPIs you can look at, cycling metrics you can look at when assessing a cell's performance, and how you do those calculations, what kind of metrics you look at are going to affect your analysis and your lifetime predictions or your modeling that you're trying to do. So certainly it's important to have the data infrastructure there where you can look at a bunch of KPIs or a bunch of different metrics really easily and understand which are the best predictors or the best metrics to use for your specific cell and your application.
So final couple of set of questions here around additional quality check methods on the incoming level. These should also probably be done on outgoing as well. That may make more sense long term. So outside of IR and OCV and others, have some questions about CT and ultrasound. And so well timed, I think in general, we view the more metrology, the better, whether it's end of line or earlier on in the process as well. The more data you have that extracts meaningful metrics, the more you're able to surface and catch some of these quality issues earlier on. And yeah, I'll let Dan, he actually led some of the integrations with some CT players and ultrasound as well, but just talk through just some of those techniques and what you could find with them as well.
Yeah, it looks like there's a little bit of back and forth here on CT. And certainly I agree, it can be costly and a bit time consuming, but CT companies have gotten really good at optimizing those collection conditions, X-ray energy and time and number of cross-sectional slices you're taking and all sorts of things that they can do to bring down that scan time to pretty reasonable levels. And there certainly are some large-scale manufacturers doing what they call 100% CT inspection on all of their cells. So I think certainly there's value there, but you need to understand what information that's going to give you and not just do CT for the sake of doing CT, because you can do it fast and with a high precision. Obviously, this is an X-ray technique. You're going to be visualizing high density defects, like one of the users mentioned, electrode alignment. The electrodes are metal, they're easy to see by CT. Alignment is really easy to check. Depending on the cell that you're choosing, cell alignment or electrode alignment may be more or less important, and that might be something that you want to dig into. On the flip side of that is ultrasound, which is going to be really good at looking for low density defects. So things like electrolyte wetting, gas voids, things like that inside the cell. And if those are things you're concerned about, you should absolutely be considering ultrasound defect detection. But again, doing it for the sake of doing it is not necessarily going to be the best practice. And so that's why, like, when you're in this qualification stage, I think it's really important to try a bunch of different things and understand what are the good predictors. So do CT, do ultrasound, pulse your cells, just put them through a ringer of different tests, then cycle them, then age them, and figure out which ones were actually useful. Did my electrode alignment turn out to matter? Did these little voids that I saw from ultrasound detection, did they actually turn into pockets of lithium plating and weak points in the cell? This is your opportunity to figure that out at the qualification stage. So do a bunch of different tests, cycle your cells, see how they age, see what are the good predictors, and then work to implement those when you go into production.
Yeah, and ultimately, if you can, plug for the next seminar, design those into supply agreements so your supplier does them. So figure out what's needed. They'll want justification for it because it adds cost, but if it makes sense, it's cheaper for them also ultimately to, if you're going to be scrapping a bunch of cells on your side, it's cheaper for them to catch them so they don't have to ship them to you. They don't have to go through the paperwork. It's a win-win here. Ultimately, the incentives are all around everyone making money and not having to deal with warranty issues, and need data to do that and figure this all out. And the more metrology, the better, in our opinion. Awesome. So I think with that, I just want to thank everyone and thank Dan for putting together most of the presentation and giving the fun demo. Feel free to reach out if people want to dive deeper into any of these topics. Thank you.
Thanks, Tal. Thanks, everyone.